Let me welcome everybody to Fusion EP Talks, a student-led webinar on fusion science and technology. My name is Tobias Jesche, and I'm delighted to introduce you to today's speakers, Vishal Twendy. Vishal is the first and his final year of PhD students in Bratislava, Slovakia, and he comes from India and completed his bachelor's in physics from the University of Delhi in India. After his bachelor's, Vishal completed a master's in physics from the University of Allahabad, India. During his master's, he has worked on project in collaboration with Selçuk University, Konya, Turkey. In 2018, he became a PhD at the Department of Physics, Comenius University in Bratislava, in the group involved in the research related to LIBS, laser-induced spectroscopy. With that, I will hand over to Vishal, and everybody enjoy the talk.
Thank you so much, Tobias, for the nice introduction. First of all, I would like to thank whole Fusion EP Talk team for the invitation. It is my great pleasure to be here and share our contribution to the fusion research. As you already see in the screen, today's topic is slightly different from other conventional fusion-related topics. So let me start the talk, and I will be happy to get some ideas and comments from you at the end of the talk. My name is Vishal Dwivedi. Basically, I am from India. Currently, I am final year PhD student at Department of Experimental Physics, Comenius University in Bratislava, Slovakia, under the guidance of Professor Pavel Weiss and co-supervised by Assistant Professor Dr. Alicia Marin Roldan. Today, we are going to discuss about laser ablation-based spectroscopic technique, laser-induced breakdown spectroscopy. In short, it is also known as LIBS, for the study of plasma-facing materials and fuel retention. During the talk, firstly, I will briefly discuss the motivation behind this work, then a very short introduction or description of the LIBS technique, and specifically calibration-free LIBS, which is known as CF LIBS, then some of the experimental aspects, and some of the results from the study of pure materials in the both picosecond and nanosecond regimes, study of fusion-relevant mixed coatings, including quantitative analysis, depth profile, and fuel retention, some of the results, and conclusion. So, firstly, the motivation. As we all are connected to the fusion research, so we already know that we are developing a source of clean energy in the form of fusion reactor, ITER, but from the physics and engineering point of view, there are selected problems which should be solved for the development of fusion reactor. Here is a small list, so we can see here. And our research group is mainly focused to the work related to the material choice for the fusion reactors. So as we already know that graphite has been used in the last 20 years for optimizing plasma requirements, but this is no more suitable for reactors because of additional requirements, lifetime, low tritium uptake, and neutron compatibility. So now we know already that ITER is considering beryllium and tungsten as a plasma-facing materials. So beryllium will be as a first wall, which is approximately 700 meters square in the area. This has been chosen because of low jet plasma compatibility, good oxygen jitter, thermal conductivity, and tungsten is being considered as the diverter material. The surface area for the ITER is 150 meters square. It has been considered because of low sputtering yield and highest melting point. And this is the image of JET, tokamak. And JET has already installed the ITER-like wall. So we can see here, beryllium, green color. So we can see the first wall material and tungsten and other materials. But what can affect first wall materials? Erosion, migration of the material in the AS plasma, deposition on the new locations, beryllium tungsten layer, accumulation of fuel in the vessel, and melting and damage. So our main goal is to understand and control the interaction between plasma and plasma-facing materials to achieve a high performance of the fusion devices. So in this work, I will present the study of ablation characteristics and compositional analysis of the fusion-relevant pure materials, so which is tungsten, molybdenum, tungsten copper alloy, and also some deposited mixed coatings, so beryllium tungsten deuterium, beryllium oxygen carbon deuterium, tungsten tantalum deuterium, tungsten zircon, and lithium-based deposited coatings, and using calibration-free laser-induced breakdown spectroscopy. Yesterday, I was curious. I was checking Web of Science, so I was checking the statistics. So these are the papers which are published with the keywords LIBS and fusion from last 20 years, 2001 to 2021. And we can see the exponential increase in the publications related to the LIBS and fusion. So we are growing. Also, in the motivation, I will mention these few remarkable papers which shows the relevance of LIBS for the fusion research. This was the review paper from last year, 2020, from our group. And this is a review of the LIBS analysis for the plasma-facing components diagnostics. Also, we had last year one invited talk from the Szeged, Hungary in December 2020. It was for International Workshop on Laser-Induced Breakdown Spectroscopy. And the title was, Why is LIBS the future online analytical technique for plasma-facing materials of thermonuclear reactors? So this was quite interesting. Now I will briefly introduce the LIBS. So as we know, LIBS is an analytical method, atomic emission spectroscopy, for the determination of elemental composition of the samples. It can be qualitative analysis or quantitative analysis, also depth profiling, elemental mapping, elemental imaging, etc. This is the basic principle of LIBS. So firstly, laser ablation. So when the short pulse laser beam is focused on the surface of the sample, a small volume of the sample mass is ablated, and this process is known as laser ablation. After that, there will be formation of plasma. So this ablated mass further interacts with the trailing portion of the laser pulse to form a highly energetic plasma that contains free electrons, excited atoms, and ions. The plasma induced by laser matter interaction emits light, which consists of discrete lines, bands, and overlying continuum. When the laser pulse terminates, the plasma starts to cool. During the plasma cooling process, the electrons of the atoms and ions at the excited electronic states falls down into natural ground states, causing the plasma to emit light with the discrete spectral peaks and spectral lines. And by identifying these different peaks for the analyzed samples, its chemical composition can be rapidly determined. So in short, we have focused laser pulse, so here, and when it is focused on the sample surface by using the lens, it vaporizes, atomizes, and excites the sample, create the plasma emission, and this plasma emission we can collect, disperse, and analyze the light, and from that we can determine the elemental composition using atomic spectral lines. So here, almost all elements from the periodic table can be determined using the LIBS. And this laser-induced plasma contains electrons, atoms, ions, molecules, and clusters. What are the advantages of LIBS? LIBS is portable technique. It has rapid analysis, little sample preparation, micro destruction of the sample. Different types of samples can be analyzed, solid, liquid, gas, or anything. Wide elemental range, so we can see almost all the elements from the periodic table can be analyzed. Light elements also can be analyzed. Depth profile analysis we can perform using LIBS, online monitoring, and elemental mapping. Applications, so there is wide range of applications from the LIBS, but basically we are focused to fusion research, and there are others also, forensic, food, space, agriculture, etc. Now the question is availability of reference samples and matrix effect from the LIBS. But for this, we have solution, which is CF-LIBS. So we will see in the next slide. For LIBS, the laser light intensity should be high enough to produce sublimation, evaporation, extraction of the particles from material, and formation of the dense vapor plasma. This is a quasi-stationary interaction process, and this is LIBS plasma image. So we can see in the hot core mostly ions, mid region contains ions and neutrals both, and cold outer region is mostly neutrals. After that there is shock wave, and here is the molten matter. This image shows the timeline of plasma emission. So we have several nanoseconds or picosecond laser beam. After that there will be plasma emission, and this plasma emission contains till several nanoseconds or hundreds of nanoseconds continuum emission. After that, ionic emission, atomic lines, and molecules. This image is highly important for the CF ellipse because for CF ellipse, we should specify the time delay and gate time to observe which lines we want to observe, ionic or atomic or what. So we should choose the time delay and gate time very carefully. And these two images are from these two references, so we can see here. So what is CF ellipse? It is based on the measurement of line intensity and plasma properties, plasma electron density and temperature, and on the assumptions of Boltzmann population of excited levels, which does not require the use of calibration curves or matrix matched standards. Historically, it is started from this paper, so 1999 Chuchi, new procedure for quantitative elemental analysis by laser-induced plasma spectroscopy. This paper tells that spectral line intensity and some statistical parameters can be used for the CF ellipse quantification. There are three important assumptions which should be satisfied by laser-induced plasma in order to use CF ellipse technique. These three are stoichiometric ablation, local thermodynamic equilibrium, and optically thin plasma. So for stoichiometric ablation, plasma should be true representative of the sample composition. For this, we can verify with this formula. Irradiance should be greater than 10 to the power 9 watt per centimeter square, and irradiance we can calculate using this formula. Local thermodynamic equilibrium, for this we have Macurator criteria. So electron density should be greater than to this particular value, where we use the temperature and energy gap of the upper and lower energy states. And this is optically thin plasma. So for this, we should verify there is no self-absorption in the spectral lines. And for this also, we have one criteria. So the spectral lines intensity ratio up to spectral lines should be approximately equal to the ratio of this, where A1, A2 are Einstein coefficients, G1, G2 are G factors, lambda 2, lambda 1 are wavelengths. So how can we calculate the composition using CF ellipse? So under CF ellipse conditions, the spectral line integral intensity can be expressed with this formula, where this I is the measured integral line intensity, C is the concentration of the emitting atomic species, which we want to calculate, and F is the experimental parameter, and some Boltzmann factor and energy and temperature. Taking log of this formula, so we get this, and we can easily compare this equation with the straight line equation, which is Saha-Boltzmann equation, y is equal to mx plus intercept. And from this, we can calculate the intercept and the slope of the Boltzmann plot, and we can calculate the concentration for the neutral and ionic lines both. So plasma temperature is being calculated from the slope, and from the intercept, we can get the idea of concentration. Now the ellipse experimental setup, this is quite easy, and we can see only we need a strong laser, and after that a spectrometer, some ICCD camera or CCD camera connected with PC, and some of the optical components, lens and fiber and polarizer. So how it works? So basically, laser beam is going through the polarizer to adjust the energy of the laser beam, and going to the sample through the lens, focused on the sample surface here, and it's igniting the plasma, and this plasma emission is being collected through the optical fiber, sending to the spectrometer, coupled with ICCD camera, and giving the spectra in PC. For beryllium samples, basically we don't have permission to work in Slovakia, so we measured in VTT Helsinki, and this is the experimental setup from there, and it's quite similar. So we can see laser, some optical components, mirror, and the lens. Laser beam is focused in the sample here inside the vacuum chamber, and collection is being done by parabolic mirror and optical fiber to the spectrometer, and all other components are related to the vacuum system and adjusting the pressure and background gas. This is the real photo. So this is the laser here. Beam goes through this path and going to the chamber here, and collection is being done this way, and here is the spectrometer. The laser was neodymium laser 1064 nanometer, and spectrometer ICCD camera, and detailed description of this experimental setup can be found in this reference. After that, in Comenius University, in our lab, we have quite simple experimental setup. We have possibility to use nanosecond and picosecond laser. We have optical components focusing on the sample, parabolic mirrors, and also fiber. So we have basically currently installed 3 different spectrometers in our lab. So VUV spectrometer, Michel, and high resolution spectrometer for different purposes. So we can see VUV spectrometer is being mostly used for detection of the light elements, sulfur, phosphorus, and etc. Michel spectrometer is being used for broadband spectra, which covers from 200 to 900 nanometer spectrum. And this is mostly using for temperature evaluation, electron density, also molecular spectra, rotational and vibrational temperatures. High resolution spectrometer we are using for trace element detection in complicated matrix like iron, molybdenum, tungsten. Also spectral line profiles for historic broadening of deuterium and hydrogen. So this is the schematic of experimental setup for simultaneous measurement for VUV and UV and also NIR range. So from 100 nanometer till 1000 nanometer. So here we have vacuum chamber. Laser beam is going through this path to the inside the chamber, and plasma is being collected simultaneously 2 paths. So one is here to the SL spectrometer, and also another through the magnesium fluoride window to the vacuum UV spectrometer. Now I will move to some of the results. So this is the very recent published article in 2021, in this last week only. And we compared the nanosecond and picosecond results for the tungsten and molybdenum. So we can see the picosecond LIBS here and nanosecond LIBS spectra. So we cannot accommodate full range spectra. We see nothing in the full range spectra. So we just cut down to show the difference between nanosecond and picosecond. And we can see the narrower lines obtained in the picosecond LIBS for molybdenum and also for tungsten for different delays, 100 to 400. And also we try to estimate ablation rates for each element and each laser regime. So we see in picosecond we have less ablation rate, here 85 and 55 for tungsten. And nanosecond we have around 200 and 300 nanometer per pulse. Also from the same paper it was published, these are the Saha-Boltzmann plots. From here we can evaluate the plasma temperature. And these are for picosecond tungsten, picosecond molybdenum, picosecond tungsten, nanosecond molybdenum, and nanosecond tungsten. And we can see if we are in the nanosecond regime, so delay is quite less, 200 nanosecond here. So we see there are very less ionic lines, only neutral lines are more. And we can observe the similar things in other figures also. These were the variation for the delay. So for different delays, we have the temperature, electron temperature, molybdenum, picosecond, nanosecond, tungsten, picosecond, nanosecond. Also electron density variation with the delay time. So we can see the variation here. Next, this was the last year published paper in Spectrochemica Acta. This was also the comparison of nanosecond and picosecond regimes for tungsten copper alloy sample. And we have the spectra here. So first one is nanosecond, and second one is B. This one is picosecond regime. We can see the narrower lines obtained in the picosecond regime. Also, we have calculated the ion abundance in picosecond and nanosecond regime. And we have here the gray zone represents temperature at typical operation conditions. So for nanosecond, the typical condition is around 1 electron volt temperature. For picosecond, it was around 0.6 electron volt. The firstly ionized species are the most abundant in the both regimes. So we can see here, firstly ionized species, this one, dotted one. And there are less neutral species 5 to 7 times in nanosecond regimes in comparison to the picosecond regime. Also, we calculated the elemental composition. So we can see here the results, nanosecond and picosecond regimes for different delays. After that, we studied some coatings. So this was the beryllium tungsten deuterium coating of 2 micrometer deposited on molybdenum substrate. And as it contains beryllium, this was measured at VTT Helsinki. Pressure was 0.5 millibar of argon. We can see the clear difference between isotope of hydrogen, so deuterium and hydrogen. And these are the lines, spectral lines, 656.1, 3. Also, this sample contains tungsten, so we can see the tungsten line also here. So we should be quite careful in the deconvolution of this spectral line to obtain the D/H ratio for the clear and precise composition analysis. We have calculated the D and H intensity with the laser sort numbers, so we can see the decrease in the signal after several laser sorts. We have also calculated the elemental composition for different sorts. So we can see beryllium in this color, tungsten, deuterium, and hydrogen. So we can see the percentage elemental concentration for first 8 laser sorts. After that, we studied the beryllium, oxygen, carbon, deuterium related coatings. We had possibility for 3 different samples from 3 different thickness. We have also calculated the ablation rate. This was measured under 10 millibar of the argon pressure. This is the real sample, so you can see the ablated one and without ablation. This is the dimension of the sample, 15 mm and 12 mm. We had the Lipps depth profile, so beryllium, tungsten, oxygen, carbon, and hydrogen plus deuterium. This was for this specific sample. And we compared this Lipps depth profile with the SIMS also, so we have here. And this line is representing the coating and substrate. We have this multi-elemental Saha-Boltzmann plot for the evolution of temperature from beryllium and argon spectral lines. And this is the deconvolution of deuterium and hydrogen line for the calculation of D/H ratio. After that, we studied tungsten, tantalum, and deuterium coating on the molybdenum substrate. It was 3 micrometer, and ablation rate was found around 176 nanometer. And this was measured at atmospheric pressure in our lab in Bratislava. This was the spectra. So we tried to measure firstly pure tantalum to see the tantalum lines. So here is in black color, this one. And after that, we tried to measure pure tungsten. So red color here, we can clearly see the difference between tungsten and tantalum lines. After that, we measured this specific coating. So we measured in air firstly, but we don't get enough signal for deuterium. So we try to measure under nitrogen atmosphere. And we can see that in this spectra, we can see tantalum 1, tantalum 2, and tungsten 1, tungsten 2 lines. This was measured for 1 microsecond delay and gate time. We have Lipps depth profile also. So tungsten, this black one, molybdenum, and tantalum. So after 17 sorts, we see that it started decreasing. So we are approaching to the substrate here. And this was the Boltzmann plot for tantalum lines. We have also for tungsten. It is reported in the paper. And this was the signal from the hydrogen and deuterium. So this was not so easy to distinguish between deuterium and hydrogen because in the same region between 0.4 nanometer, we have 5 different lines. So deuterium, tantalum, hydrogen, tungsten, and tantalum again. So we did the simulation and subtracting other lines from this region to calculate deuterium area and calculate the ratio between deuterium and hydrogen. So this was not so easy task. After that, we had some measurements from tungsten, zircon, deuterium also. And this is a finally accepted paper. It will be soon online. These are the spectra, nanosecond regime and picosecond regime. We have measured for low fluence and high fluence in nanosecond regime. And here is again the deuterium hydrogen line. We also have tungsten here, the convolution here. So we should again be careful. And here are the elemental compositions. So we can see tungsten, zircon, copper, and lithium and deuterium. So for different laser sort numbers, second, third to 15 this is accumulation, and 10 to 14. After that, we had some samples from Compass tokamak from Prague, and these were the screws demounted from the tokamak and from the different positions. So we have analyzed the different screws, 10, 15 screws, and we had quite good results from the Lipps measurements. This was the dimension of samples, so 1.5 centimeter the head of the screw. And we can see there was chromium and lithium because this was from the lithium campaign, the sample. And we can see the decrease in the lithium. So after sort 1, sort 2, increase in the lithium and decrease here in chromium. This was the screw number 6, which was this figure. We have also multi-elemental Boltzmann plot and also separate Boltzmann plot for the evaluation of temperature. And this was published last year in Nuclear Materials Energy. So conclusion, LIPS is suitable for future online analysis of material migration and fuel retention in materials, suitable for fusion reactor diverter valve. In general, it has been shown that the careful analysis of LIPS spectra at Balmer alpha line near the H alpha line, deuterium tritium allows to distinguish the spectral contribution of the hydrogen isotopes, which is deuterium and tritium, enabling to apply the CF LIPS technique, including the quantification of these hydrogen isotopes. So we have possibility of intermediate and atmospheric pressure, CF LIPS depth profile analysis, CF LIPS migration and impurity analysis of mixed layers, fuel retention depth profile, CF LIPS analysis in beryllium tungsten, beryllium oxygen carbon based materials, CF LIPS migration analysis of liquid material diverter material over tokamak, which was the lithium based deposits. Picosecond laser application leads to smaller ablation rates and so higher depth resolution for the quantification. Owing to advantage of remote and online analysis, LIPS is being considered to be deployed in ITER in the form of robotic arm. These are some of the recent, from the last 2 years, the publications from our group. So this was the review paper. So picosecond, nanosecond comparison, quantification of beryllium tungsten coating, quantification of beryllium, different coatings, beryllium oxygen carbon, lithium samples, and also here is the picosecond, nanosecond comparison. And this was the talk which I already mentioned in the first slides. These 4 papers are upcoming. So I think in few days or few months, you will see in online. So this is the paper from the fusion community with our participation, but it focused only the LIPS-based diagnostics. And this is the tantalum coating, so tungsten tantalum. Here we have tin-based alloys and also tungsten-based material, tungsten zircon. So acknowledgement, financial support from Eurofusion Consortium with the grant number, Scientific Grant Agency of the Slovak Republic, Slovak Research and Development Agency, and Comenius University. Thanks to our external collaborators in fusion research, so VTT Helsinki, Tartu University Estonia, Jülich Germany, DIFA Eindhoven, GSI Slovenia, Bucharest Romania, and Prague Czech Republic. These are the members currently involved in our fusion research in our group. So my supervisor and other colleagues, thank you for your kind attention. So if you have any comment, question, you can ask me now, and also you can write in my email ID or any other platforms, ResearchGate, Facebook, LinkedIn, anywhere. And also I would like to mention, highly motivated students can contact for PhD and postdoc positions at our department. So we can directly contact to our supervisor, Professor Pavel Weiss. Here is the email ID. And with this, I finish my talk. Now waiting for suggestions, comments, and questions.
Thank you very much, Vishal, for your talk, and really, really interesting. Yes, to continue what like Vishal said, now is the Q&A session open. Well, until there are the first question coming in, maybe I will start to ask
Sure,
if you don't mind.
Yeah, sure.
Yeah, perfect. It was quite in the beginning, you said there are like some elements are not possible to detect using LIPS. Which are they and why can't you detect them? I didn't get that point.
No, I think I mentioned I will go to the slide.
Yeah, it was like through a search. Maybe I understood it wrong. Because I saw like the periodic table, and for me it looked like everything was marked, but I wasn't sure.
I mentioned there that LIPS is possible for wide elemental range. Mm-hmm. So that means it covers almost all the elements from the periodic table. But I think you misunderstood in this slide where I mentioned that beryllium was not possible to measure in our lab. So we did the measurement in VTT Helsinki. So it is just because of permission. So we are not allowed to work with beryllium related sample. But in principle, it is okay to work with any kind of sample, any kind of elements with the LIPS technique.
Yeah, it just depends like on the laser and what you are able to detect and like what's the safety measurements around, right?
Yes. So you should choose your detector, spectrometer wisely what you are going to detect, and also the energy and fluence of the laser. So that is sufficient for the LIBS.
Perfect. Well, I see from Matthew writing, there's a question.
Sure.
Please go ahead.
Hello, Vishal. Thank you very much for the talk. It was really interesting to see. I work in lasers myself. Do you know how this spectroscopy and sort of compositional analysis technique compares with, say, another common technique like EDX is the one that I'm familiar with in like an electron microscope, where an electron beam excites these transitions. And it seems to be very widely used for sort of compositional analysis. And I was thinking of comparison between this with the laser excitation in the plasma versus that quite established technique in the electron microscope. If there's any differences in the sensitivity, I'd love to hear your thoughts.
Yes, so I will answer you. I'm moving to this slide here. So basically, these measurements were done for LIBS, but at the same time, this sample has been studied with other established techniques, NRA, TOFFERDA, and IBA, and SIMS also, SIMS dipset profile. Here you can see the one example. More detailed results are already included in this paper. So we have compared our results with other techniques, of course. And recently we are working with this coating, tungsten, tantalum, deuterium. And we have very good agreement with TOFFERDA and also XRF, also glow discharge optical emission spectroscopy. So I have results from other colleagues, other collaborators, and we are doing LIBS and we compared the results and we are in very good agreement with this. I hope I answer your question. So if not, so you can again ask. Detailed comparison of among the techniques were already in the papers, so you can find easily.
Thank you. Yes, no, I'd be interested to see the comparisons. It seems a little harder to guide an electron beam into a fusion reactor than a laser. So I think the advantage in sort of with regard to sort of in situ deployment would be quite.
We did the comparison, but unfortunately, I did not put in this presentation. So details are already published in the papers. So maybe it would be better to go through the papers. I don't know. I don't want to share now. I don't know how can I share the paper, but these are the references so you can see easily. So these are the papers already in comparison with other techniques. So IBA, SIMS, and NRA, and also TOFFERDA. So different techniques.
Fantastic. Was one of those papers applying the LIBS in situ inside a tokamak?
Actually, we are not working with the in situ because, as you know, we are in Bratislava and there is no tokamak here. So sure. We are not working in situ analysis. We are doing post-mortem analysis of the samples. So these are some of the simulated samples, also removed samples from the Compass tokamak from Prague. Also, we have some samples from Jülich, not Jülich, Windestein 7. And so we have different samples from the after deuterium loading and before loading. So we are trying to elemental analysis, post-mortem analysis. Also, we had some samples from Magnum PSI also. Any other question? If not questions, so please suggest some ideas or remarks or comments or anything.
If there's no other questions, I would really love to pick your brains on something that relates to my work. And hopefully to yours as well. I work in the realm of laser ultrasonics, so inducing ultrasonic vibrations inside materials from the laser illumination on the surface, and then also reading out the return echoes from deep inside the structure using a second read laser on the same surface. And I'm very interested in the future prospect of a unified diagnostic system for deployment inside fusion reactors, where by exploring variable regimes of laser power, we could potentially, in the ablation regime, perform LIBS and analyze the composition of the first of all materials. But in just the thermoelastic regime, we can perform non-destructive laser ultrasonic scanning for detection of subsurface defects. and for the monitoring of the integrity of subsurface features such as cooling channels in an actively cooled first wall. And I don't know if it's something you've come across, laser ultrasonics, but I'd love to get your thoughts on whether you think that sounds like a feasible system, whether there's enough flexibility in the variability of the illumination power to move between a thermoelastic regime to an ablation regime, and yeah, just if it's something you've come across before, or if you think it sounds like a good idea. I'm a first-year PhD student.
Sounds interesting. I see there is one raised hand.
Yeah, please, Pavel, if you want, you can unmute yourself and ask the question.
Hi.
Okay, hi. So thank you for giving me the possibility to ask. So my question, like I am a Vishal supervisor, and my question is to Matthew Riding. So like I was looking your profile in the STEP group in the Oxford. So you are working probably in Coulomb. And I looked that you are working with the metals like tungsten, molybdenum, but also niobium and vanadium. So for the plasma facing components, do you have like already some ideas about the alloys or mixed layers? How many niobium or vanadium should be inside? What could be interesting for you for doing eventually calibration and reanalysis of these mixed layers of these BCC metals, or not yet? A question on Matthew.
Sorry, I keep turning off my microphone. Thank you, Pavel, for your question. I was previously collaborating with Coulomb. I'm no longer directly collaborating with them yet. This was during my master's project. But I think all of the layers that you've studied are the ones that I think they would be interested in, and that my previous research group was interested in. When I was at ITER, there was definite interest in exactly the layers that you've studied, with the hydrogen isotopes combined with redeposition of beryllium and tungsten. The previous metals I was studying were mostly because we were just interested in the crystallography of the BCC lattice, and in some cases it was easier to study some of the materials that aren't necessarily under consideration for direct first wall application, like niobium and vanadium, but they have other properties that make them slightly less favorable when compared with tungsten for an actual first wall application. But I wouldn't like to overstep my bounds. I no longer collaborate directly with Coulomb, so I'm sure you should get their confirmation on that one. But yeah, it looks like the materials you've been studying, the layers you've been studying are the real ones of interest with regard to ITER, and then moving forward to full tungsten walls and things like that.
Perfect. Matthew, I also got like a question, like a comment from Mauricio Gago concerning like this topic on EDX, and he mentioned that it's a big difference from EDX. It's like more superficial analysis, whereas LIBS can detect the composition deeper into the sample because it aberrates the surface. So you can have like a depth resolved analysis. That was something he brought us, and I wanted to share with you. Yes, if there are no more questions or comments right now, I would first like thank you again, Vishal, for your presentation. And
it is my pleasure. Thank you so much, and Fusion EPTOC team, who invited me.
For sure.